Okay,
Okay.
thank you very much.
Yes.
So I would
Okay.
like you,
Started.
yeah, to join me on a journey that I did over the last 2 years, a journey searching for short duration meteor showers. And if you do so, I promise I will also share with you 5 things that I learned during this journey. Outline of my talk, I will give a brief introduction of what we are doing and why I am doing that. Then I will talk or show a few slides about the algorithms that I used for meteor shower detection. I will give you some numbers of the analysis, and then the primary part of my talk, which is a little longer than the other ones, is on the number of meteor showers which were detected. So what I'm talking about here, that's a Meteor database which is collected by the IMO Video Meteor Network. That's actually the oldest network, the longest one that has been in continuous operation. So we have, meanwhile, over 20 years of continuous video meteor observation. And since June 2007, there's not a single night where we didn't have any meteor recorded. Currently, the network has been relatively stable over the last 5 years with about 40 observers running about 80 video cameras, primarily in Europe. We have some in the America, but this is primarily centered in Europe. And so far, most of the analysis of this network is single station analysis. Why is that? Because, I mean, nowadays everyone has big networks. Nowadays everyone is multi-station observation. Well, primarily because in the beginning, the cameras were relatively far apart. So there was just a little overlap between these cameras. Well, that has meanwhile improved a little with these 80 cameras, but still it would be just a small percentage of meteors if we just go for double station observation. Whereas if I do the single station analysis, really every meteor counts, and it also makes some things easier. So for example, you do not need to synchronize between the cameras. Of course, it has certain disadvantages, but this is maybe the primary reason why this kind of analysis is still based on single station analysis. And the kind of meteor shower search that I want to present is has already also some history. So the first time that I presented this type of automatic meteor shower search was published or presented at the 2006 IMC in Roden in the Netherlands. By that time, the database was almost 200,000 meteors, and for the first time, I applied these algorithms. I developed and applied these algorithms to automatically detect meteor showers in this database of single station meteors. 2 years later in Zashitica, I presented the next analysis. The database size had almost doubled. On the occasion of the 10th anniversary of the IMO network in 2009, we did another analysis and detected a number of new meteor showers. The last big analysis of this type was on the occasion that we recorded about 1 million meteors. That was presented in Poznan at the IMC 2013, and by that time we could really present a list of over 100 meteor showers which were detected in this database. And now, on the occasion of the 20th anniversary at 2019, I saw that that is a good time to repeat the analysis. Our database had grown, meanwhile, by a factor of 4. So we have like 4 million meteors. But the idea was not now to just repeat the same analysis. So this time I have changed something. And what I changed is actually the resolution. So far, the resolution was that I analyzed always solar longitude intervals of 2 degrees length and with 1 degree shift. And so that means if to detect a meteor shower, it must be present at least in 4 or 5 consecutive intervals. So in these analysis, I would have only detected meteor showers which last at least for 4, 5, or 6 days. And as I said, instead of repeating this, I have now increased the temporal resolution. So the new analysis that I will present today has a duration or a bin length of just 0.2 degrees solar longitude with a shift of 0.1, which means we have a 10 times increase of the temporal resolution, and we can detect much shorter meteor showers. So in some respect, we have like the same number of meteors per bin as we had 10 years ago with this analysis in 2009, but we have now a 10-fold increase in the temporal resolution, and that gives us the chance to detect meteor showers which are much shorter. And this is what I want to focus on today. So how does the meteor detection work in the single station work? Well, in double station observation, it's fairly easy. You observe the same meteor from 2 stations, and then you have directly the trajectory of the meteor, and that gives you directly the radiant and the meteor shower velocity. Well, if you have just single station observation, then it is more complicated. So here's your meteor. You can do the backward prolongation, and then somewhere in your right ascension declination space, in the backward prolongation, there is a meteor shower radiant. So you have here some probability distribution. But you do not know, obviously, the velocity of the meteor shower. So, I mean, if it was a slow meteor shower that you have observed here, then the radiant is farther away from the meteor. If it was a faster meteor shower, then the radiant or the probability would be closer to the meteor. So in fact, it's not just a two-dimensional problem that we are talking about, that we have to search the radiant in right ascension and declination, but the third dimension is a meteor shower velocity. And this is effectively what I'm doing in this radiant search, which is the first step. So first of all, I take my bins. So I cut the whole 360 degrees into pieces of 0.1 or 0.2 degrees solar longitude. And then for every meteor inside the solar longitude interval, I calculate the probability of all the, and these radiants, I mean, this is just right ascension declination, the radiant position, but I calculate it also for all possible velocities. So we have like a cube, like a 3-dimensional probability distribution. And once I did that for all the meteors in this solar longitude interval, then I look for peaks, for maxima in this cube here. And these peaks then correspond to meteor shower radiants or possible meteor shower radiants. So they give me the right ascension, the declination, and the velocity. And that procedure is then simply repeated for every single solar longitude. So starting by 0.0, 0.1, 0.2 until 395.9. 359.9. And so I get for each solar longitude interval possible radiants. And then the second step is to find similar radiants in subsequent solar longitude intervals, because these are then my meteor shower hypothesis. All right, before I start this, of course, I have to decide which kind of distribution I use here. So it could be a Gaussian distribution. It could be like an exponential distribution. Well, the best thing is not to guess. The best thing is to look at your data. And I did that again. This distribution type is derived from the maxima of major meteor showers. And what I found here is that in the latest analysis, for the position error distribution, it is good to take some Laplacian or exponential distribution type. And for the velocity, I see more like a Gaussian distribution. And this was used during the analysis. And the thing that I want to point you out is, it's hardly visible, but there's a little dip here, close to zero error. So you see, we see less meteors which have really zero error then the fitted distribution would tell us it's the same both for the position distribution and for the velocity distribution. You see also here there is some lag. And I was curious, I mean, is it something which I only see? And this exponential versus Gaussian distribution, what do others see? So I approached Sonota Ko, who has just published analyzed and published his latest data set from the Sonota Ko network. And he was so kind to provide me a graph with the error distribution that he sees. So this is his position error distribution and his velocity error distribution. You see the distribution is neither Gaussian nor Laplacian, so it's something intermediate. But the thing that I want to point out is that interestingly he sees the same effect. So for some reason he has a dip towards very, very small errors, 0 or 0.1% here, or here in the velocity distribution. And this is something where I have no explanation for so far for this behavior, but at least this would be my first finding that something strange is going on here, which deserves a closer analysis. Why do we have there a lack of meteor observation, really with very, very small errors, both in position and velocity? That was my finding number one. Now let's get to the analysis. So this is a database. We have overall, as I said, more than 4 million single station meteors collected between 1993 and 2019. So as I said, on the occasion of the 20th anniversary, the analysis was conducted. I said that with a bin size of 0.2 degrees solar longitude and a shift of 0.1. And that gives me for each of these 3,600 solar longitude intervals between 400, that was a minimum, and almost 21,000 meteors per solar longitude bin, and the median was something like 1,500 meteors. So that's quite a solid database. And in this graph, you immediately see the major showers of the year. But let's proceed. Again, about the analysis, the parameter set that I have chosen, I have sampled the parameter space, so the position with a step size of 0.5 degree, and the velocity also with a step size of 0.5 kilometer per second, and that gives me an overall of 18 or more than 18 million possible radians, which are to be calculated and checked. And because we have these overlapping bins, each solar longitude bins, each meteor counts into 2 bins, and I have 2 iterations during this radian search. Well, each of these radians had to be calculated 4 times, and that gives in total 70 trillions radiant probabilities that I had to calculate during this meteor shower search. And you can imagine this is something which you do not do in a minute and in a few hours. In fact, it was like 10 CPU years that I consumed for this search. Well, it didn't take me 10 years. I used 6 CPU cores in parallel, but still it was running for 18 months. So I started the calculation in spring of 2019, and I finished it only late last year, early this year. And I also had to do some optimizations. My radian search program failed for some strange reasons, so that was some insight. I won't go into detail here, but I learned also I improved the radian search program. And in the end, I came up, I have these 3,600 solar longitude bins, and for each of them, I calculated up to 50 possible radians. And that gives a total, as a result of the first part of this analysis, of about 180,000 possible radians, so radiant candidates, in the course of the year. And then the next part was to search these 180,000 possible radians, find radians in solar longitude intervals close to each other, which then form chains of radians. And these are my meteor shower, possible meteor showers. This was there was an algorithm used, forward-backward algorithm, to connect these radians. There could be also other methods that were suggested, like hidden Markov model or machine learning, that would be worthwhile to try on this large number of radians. But I used this deterministic approach, and I run the analysis with relatively low thresholds. So I had in the end a quite large number of meteor shower candidates. I'm sure that at least half of them, even more, are false positive, but still I run it with these low threshold to be perfectly sure that I really grab these faint and short meteor showers that I was looking for. And in the end, by the way, almost 10% of these 180,000 radians were actually assigned to some shower. And now we come to the results. Actually, my litmus test was, would I detect the October Cameloparda leads? So that was really my test if the algorithm was fine. And that's a well-known shower. It's a very short shower, lasts for less than a day. It's established. And the question is, would I find it? And the answer is yes. I found this shower. We will get back to that in a minute. So I will not yet describe the details of this shower. I will first describe to you this table here, because I will now present the next meteor showers in the next slide, always in the same way. So what do you find here on the slide? In the first part, you have the table, which has 2 lines. The first line is the one from my analysis, and this is shower number 17. So this means this is the 17th strongest shower out of the 350. So it is a relatively strong shower. The second line gives the reference values from the MDC meteor shower list. So you see here, this one was detected as OCT, shower number 281. Then we have information about the activity interval, where I detected the shower both in solar longitude and in the date. The number of meteors which were assigned to this meteor shower, the position of the radiant at maximum. So first of all, no, sorry, it's not the position, it's the time and the date of the maximum when the meteor shower was detected. The activity, that is a relative value. It's an arbitrary unit. It is more or less the probability which was accumulated from all these individual meteors, and calculated by hand also the full width at half maximum, so the duration of the meteor shower. And then you will see different graphs. Here in the left is a rank of the meteor shower. What is a rank? Well, for every solar longitude, I'm sorting the radiants that I find, and the strongest one gets number 1, the second strongest number 2, the third strongest number 3. So if the rank is low, it means it is a very strong source. So here, for example, we see it started in the solar longitude interval 192.2 with rank 5. So it was a fifth strongest source. Then it was shortly, for a short solar longitude interval, the strongest source in the sky, and then it was weakened again. So that's what the rank means. Over here, we have on the right side, the activity, and the activity is measured in 2 ways. A green graph, that's the stupid plain number of absolute number of meteors, which were assigned to this radiant. And the red graph is some normalized activity index. So it's not just a meteor number, but also normalized against the overall number of meteors and some observability function. In the lower left, we see the position of the radiant over solar longitude, right ascension declination, lower middle, the same thing in ecliptical coordinates, so sun-centered solar ecliptical longitude and ecliptical latitude. And in the lower right, we always find the velocity. Okay, so before we now have a look at the showers, I wanted to dive one thing in more detail. I was curious if this activity profile that I present from the plain number of meteors, how good that would be. And for this, for the October Carmelo paralids, I compared it with a flux density profile, which I would get out of meteorflux.org. And to my absolute surprise, they were aligning very good. They were aligning nearly perfect. And why is that a surprise? Well, I mean, remember that this red and this green graph, there is no correction for anything. It's just a plain number of meteors, no observing time, no number of cameras, no field of view, no limiting magnitude. I mean, that can change from one solar longitude interval to the next. But still, if you observe over such a long amount of time, it will all average out. And the profile that I get just by looking at the plain number of meteors or by this simple normalization looks, at least in this example, very good to a really high profile flux density. And before I go to the next shows, one more remark. I omitted all the anti-Helian and apex sources or showers which were close to these because there are a number of streamlets at this position, and that would really be waste. So let's start with a simple example, still a relatively long shower, the Gamma Ursa Minorids. Okay, I have already heard about it, active at some time in mid-January, and the activity profile, well, it's pretty okay. So you see it's a rise, we have some maximum, we have some fall, but I mean, of course, 3 degrees solar longitude, that's not yet really a short shower. So let's go for shorter ones. So this one I have never heard of, June Rose Signids. But if you look at it here, in particular, at my rank between 83 and 85 degrees solar longitude, that's somewhere in June. That's the strongest radiant in the sky for almost 2 degrees in solar longitude. So we see here the full width at half maximum is about 2 degrees, and here's our activity profile. So it's not really that nice, but still it looks like a profile. Also here the scatter and parameters, it's still okay. Maybe here in right ascension, we see some larger scatter. So that's also a fairly stable detection. Okay, so we have the next one, which is just 2 degrees in solar longitude, Alpha Corona Borealis. Well, let's jump this one. You know, the activity profile, that's not really nice. We have nicer ones. Have you ever heard about Southern Lambda Draconids? No, I didn't. But still, and this is also a particular example, this is a shower which can be detected relatively safe, but it was never the strongest source in the sky. You see the rank is never going beyond 5, but still, if I look at the radiant position, I mean, that matches relatively well. We have a really good, consistent radiant position, and also the velocity is relatively stable. So it's this shower, which is detected in early November, is also relatively safely detected. And it was with a duration of almost 2 degrees. So now we are approaching showers which have a duration of 1 degree. So we have the January Xi Ursa Majorids, again, something I never heard of, active in mid of January. And you see again, there's a very short interval in solar longitude between 298 and 299, where this is the strongest source in the sky. It's overall like 800 meteors, so this is quite nicely detected. And the activity profile, well, that's also, it's maybe not like in a textbook, but it's acceptable. So that's also a fairly good detection. And now we are getting to the showers which are shorter than 1 degree. So here we have the February Eta Draconides, as the name says, active in February. Once more, we have a short time around 315 degrees solar longitude when this is the strongest source in the sky. And you see we have a very nice activity profile. So that's what I expect from a good meteor shower. Only 400 meteors which contributed to this one. And the duration is, at least the duration full width at half maximum, is less than 1 day, less than 1 degree solar longitude. So can it get any shorter? Yes, it can. The next one is a Psi Andromedes, a shower which is detected in early June. Once more, for a very short time interval, it is the strongest source in the sky. If we have a Venner full activity profile, even though it's just 120 meteors which contributed to this particular shower, it has a nice symmetric, so it has a nice rising and falling edge. So once more, a very nice detection with just a duration of 0.8. And it can be even shorter. Let's have a look at the Mi Epsilon Cygnets. Never heard about them before. Just 170 meteors in the whole analysis. But once more, a relatively nice activity profile and a duration of just 0.7 degree solar longitude. But that's still not the shortest one. Let's proceed. We have the June Epsilon Cygnets. Once more, as the name says, it is active in June. It's like 600 meteors, 700 meteors, so it's very well given in our database. It is all of the time the strongest source in the sky, and then suddenly it appears and suddenly it disappears. And here we see the activity profile, also very nice. So this one is definitely a safe detection, which in duration of just 0.7 degree. Well, that's still not the shortest one. Now we get to the October Draconids. We are almost at the end of the short meteor showers. October Draconids, well, I mean, that is a little cheating, because we know that they have sometimes short duration outbursts. And if they are set outbursts, they have a tremendous activity. And then, of course, if I calculate the full width at half maximum, this is relatively short, but because it's primarily the outburst, maybe if we take also the slopes, side lobes, it's a little more than half a degree. But that's definitely a very short meteor shower. And we have another one with a duration of just half a day, which is a June Iota Pegasids. They're active by the end of June. Once more, we have recorded over 600 meteor. Actually, this is shower number 13 on my list. So this is one of the strongest showers which is detected overall in the list. Most of the time, whence it visible around solar longitude 94, it is source number 1, so the most active source. And you see a wonderful activity profile, very steep. And for this reason, it has this short duration of just 0.5. And then we come to the last two. So the ones we talked already about, my favorite shower, the October Camelopardalis, with this perfect profile, with this perfect activity profile, just active at a very short time. So just 0.3 to 0.4 degrees solar longitude, where the strongest source in the sky, and then they suddenly disappear. And the number one, the last one on the list of the shortest showers, the July Gamma Draconids, Peter's favorite, Peter Brown's, because it's a GDR as abbreviation. Again, this is a little cheating because we know that they had some outburst, and this outburst is well visible here. And if I calculate the full width at half maximum of this outburst, it's of course very short, but also this shower can be nicely detected. We have some background component here. It's definitely a short meteor shower. Which brings me to the summary of my talk. Well, actually, so did I find something unknown? Well, when I did the first analysis, about half of the meteor showers were unknown because I was using the MDC list of 2012. But then I loaded the latest list, and you've seen all of them have already the name. So my finding number 3 is I want to give a congratulation to Peter Jeniskins and all the other researchers who are operating these major camera networks, because their equipment and their search is already that good that also really these short duration meteor shower do not escape them. So half of the meteors or the meteor showers that I just presented to you were detected over the last 5, 6, 7 years. So very well done. Congratulations from my side. That's a good job. And another finding here that I want to give you here is that interestingly, most of these short showers do either show up in January or June. I have no explanation for this at this point. It's just an observation that I want to make you aware of. They are not evenly distributed. There are certain times of the year where it seems at least to be easier to detect these kind of showers. And now I believe I have just 2 or 3 minutes left. So I will give you at least a very, very, very short glimpse on the major showers. I will skip a number of slides because the interesting thing about the major showers, and I will show you 2 or 3 examples, is that I can follow them for an extremely long amount of time. So for example, the Geminids, I can track the Geminid as early as November 28, and I find them until December 19. You see in the beginning, the radiant is quite weak. In the end, of course, it's getting weak again. But if I look at the parameters, that is still acceptable scatter, both when I look at the position of the radiant and when I look at the velocity. So it's really amazing. And the same happens with all the other major showers. So take the Perseids, for example. I can track them starting from as early as June 12 until September 03. You see, of course, in the end, well, we have some major scatter in the parameters. So that may be in question if really the Perseids can be seen until early September. And we see this little dip here in the activity profile, the well-known in mid-July, that could be the overlapping with the Zeta Draconids. But it's again amazing how long these showers can be tracked. So I will briefly skip the next one because I'm running out of time. Leonids, Orionids once more, extremely long, but here indeed it seems that the radiant is merging with another source. You see this is the time here on the right side where the radiant is clearly the Orionids, and then we have a sudden change in ecliptical latitude. So that's probably a different source which is merging them into the Orion. It's probably not the Orionids anymore. Okay, Lyrids not so interesting, Photontids not so interesting. Eta Aquarids really great because you see them all through April 27 until May 23 for full months, and they're always the strongest source in the sky. And we have very small scatter in the parameter, so that's really one of the safest showers that we have, the Eta Aquarids. Oocytes, let's jump them. So this is my, here's a short summary of the major showers. This is my last slide. So my last finding, okay, I skipped this one. The last finding I wanted to share you is really that the major showers can be tracked much longer in time that I expected and that we know from the typical meteor shower list, which again, I find is an interesting finding. And as a last slide, all the data that I've presented, I have put them now onto the homepage of the IMO network. You find there both the radiant list for all these solar longitude intervals, and you find also these showers, these 350 showers, which of course deserve a closer look up because there are a number of false positives in there. And what I will do after a final manual consistency check, I will also send these to the MDC Meteor Shower Database that we can populate the lookup tables for the meteor showers, because with this kind of analysis, we know exactly where the meteor shower radiant is located at a certain point in time. And with that, I would like to conclude my talk.